In this presentation, we're going to define a new quantity called impedance, and it's really just a different way to write the resistance of a resistor or the reactance of an inductor in such a way that we're going to be able to add resistors, inductors, and capacitors together in an AC circuit and be able to analyze them and figure out what their currents and voltages are when they're connected in series and parallel. So we've already sort of implied that the reactance of an inductor is a measure of how much that inductor resists the flow of electricity or resists the current that's flowing through the device. And so to more formally define a quantity that opposes the current in a circuit, we define something called impedance. And so impedance is going to measure how much a particular current element resists the flow of current through the device. And so how much does it impede the current that's flowing through it? So we define impedance as a capital Z, and you'll notice that it is, in this case, bold. And that's because impedance is going to be written as a phasor. And so when we look at impedance, we can rewrite Ohm's law for AC as V equals I, and instead of R, we have this new property called impedance, Z. So V equals IZ, which is essentially the same as Ohm's law. So Z is going to be our measure of how much that component resists or impedes the flow of current through the circuit. So we could rewrite this as the impedance is equal to the voltage over the current, where all of these are now written in phasor notation, and impedance is not just a number, like number of ohms, but it's also going to tell us how, for a particular component, how does the voltage and the current relate to one another in terms of does the current lead, does the voltage lead, and by how much. So if we write this in phasor notation, our impedance can be written as a complex number. So in phasor notation, the voltage would have some magnitude or amplitude associated with it. The current would have some amplitude, and there would be some phase angle between the voltage and the current. And so impedance is just the amplitude of the voltage over the amplitude of the current with the phase angle between these two components. So over here I have a picture. I have some box that contains something. It could be a resistor and an inductor. It could be just a resistor. It could be an inductor and a capacitor. There are components inside here that have some overall impedance. There's some current that's entering those components. There's some voltage that's developed across them. This voltage and this current may not be in phase with one another, and in fact the phase difference is an angle theta, so that the voltage in this picture right here leads the current by an angle theta. So we can also write this in terms of just normal phasor notation, that the impedance has some magnitude associated with it, and then it has some phase angle associated with it, where the impedance magnitude is just the voltage over the current. And since the voltage over the current is typically written as the it's typically written as the amplitude of the sinusoidal varying voltage over the amplitude of the sinusoidal varying current. But both of these amplitudes depend on the effective values of the root mean square values by a factor of the square root of 2. If you put those values in, it's also the same thing as taking the root mean square values and dividing them. So when we find that the value for the impedance, sort of using the equivalent of Ohm's law in terms of its magnitude, it's just the voltage value over the current value, regardless of whether we use the maximum values or the amplitudes or the effective values. So let's think about this in a little bit more detail. Let's go back to what we know about resistors. And so what we know, if we have a purely resistive device in our circuit that the voltage across the resistor and the current through the resistor are in phase with one another, right? They have exactly the same phase angle, and when one is a max, the other one is also a maximum. If we write these in phasor notation and we calculate the impedance for a purely resistive component, that would be the voltage across the resistor divided by the current, equivalent of Ohm's law. The voltage across that resistor has some amplitude associated with it, which I wrote as VR here, and a phase angle, and I would divide it by the current, and this has the same phase angle. So in terms of phasor notation, if I were to divide here, theta minus theta would give me an angle of 0, and the voltage across the resistor over the current just gives me the resistance. So I can write down for a purely resistive component, the impedance for a resistor is just whatever that resistance value is, and it has an angle of 0 degrees. And so I can write that in terms of complex numbers as just having a real part, and that real part is just the resistance in the circuit. So this is pretty straightforward because Ohm's law, V equals IR. The resistor is very different than a capacitor and an inductor in terms of what it does in the circuit. Now let's think about an inductor. So we know that with an inductor, the current lags the voltage by 90 degrees. So the voltage across the inductor can be written as sine omega t. The current through the inductor is going to have some amplitude times sine omega t minus 90. So if I wanted to calculate the impedance for an inductor, I would use the voltage over the current. This is the voltage of the inductor over the current of the inductor. The voltage of the inductor, the amplitude would be Vm. I wrote it as VL here, and it has a phase angle of 0, and I would divide by the amplitude of the current, should have been Im here, and then with a phase angle of minus 90. Using phasor notation, if I divide 0, and then I wanted to figure out the angle here, I would take 0 minus a negative 90. That would give me a positive 90. And I know that the voltage across the inductor divided by the current of the inductor is this component that's called the reactance. So the impedance of an inductor is the reactance with an angle of 90 degrees. Remember, the reactance is essentially very similar to resistance. It's measuring how much that device resists the flow. And the impedance is just telling us what is that reactance value, and then also what is this phase angle. So what does this 90 degrees mean? With impedance, the angle is basically telling us how does the voltage compare to the current. And this is saying that the voltage leads by 90 degrees, or that the current lags by 90, but it's easier to say that the voltage leads by 90 degrees. So the angle for the impedance is always going to tell you how does the voltage compare to the current that goes through that particular component. And of course we can write that in complex numbers. If it's in complex numbers, if this is 90 degrees, then the real part is 0, and the imaginary part is just the value of the impedance. And of course, there's our reactance again. It's just the angular frequency times the inductance. All right, let's try to work an example. Let's use the phasor notation and the impedance values. So I have a circuit shown here, and I want to determine what is the current in the circuit, and then I want to also sketch the phasor diagram, and I want to sketch the waveforms. So the very first thing that I would want to do is I would want to figure out what the impedance is for that particular resistive component, and I know that it is just a resistor, and so the impedance is just the resistance value of 2 kiloohms, and the phase angle is, or the angle is just 0, so it only has a real part because it's resistance. I would want to write down what the phasor notation is for the voltage across the resistor, so I would take the amplitude, and I would divide by the square root of 2 to give me the effective value, and then I would put in what the angle, the phase shift angle is, which is negative 40. So in phasor notation, I could write the voltage across the resistor as 4.24, with an angle of negative 40 degrees. I can now use the equivalent of Ohm's law, that the current the current through the resistor is just the voltage across the resistor over the impedance of the resistor. So that's 4.24 volts, angle of minus 40, over the impedance, which is 2 kilo ohms, angle of 0. 40, negative 40 minus 0 is just negative 40. 2.24 over 2 is going to give me 2.12, and it's volts over kilo ohms, so that's going to give me milliamps. I can convert that back into a sinusoidal varying source for the current through the resistor by taking the effective value and multiplying by the square root of 2, and then putting in sine omega t, and then putting in that phase shift of negative 40. And then I get square root of 2 times 2.12 is 3 milliamps. So my current is varying sinusoidally. It's in phase with the voltage supply, right? Negative 40, negative 40. And I have figured out what the current is, which is 3 milliamps. It seems like there's a lot of work to get to this answer, because essentially you could have taken this number, divided by 2 kilo ohms, right? Current is voltage over resistance, and I would have gotten 3. So I understand that this is a lot of work to get to this answer right here, but I wanted to go through the steps because eventually when we get to more complicated problems, you're going to want to follow these steps regardless of the component that you have in the circuit. So if I was going to represent these as phasors and also in waveform, I would have my voltage, which has been shifted to the right by 40 degrees, and I would have my current, which has also been shifted to the right by 40 degrees. And then in phasor notation, both of the voltage and the current would appear 40 degrees below the axis. In my picture, the red is representing the voltage and the blue is representing the current. And I can represent, of course, my phasors. I should, I guess, write down what they are and put those values in my picture as well. Suppose we went through the same type of a question for an inductor. So in this particular case, I want to use phasor algebra to find the current that's flowing through this inductor. I'm going to sketch the phasor diagram and the waveforms. And what's given to me is that this inductor has an inductance of 0.5 Henry, and that the source is oscillating in such a way that the inductor has a voltage that's oscillating at 50 radians per second. This is important for us because we're going to have to find the reactance. So the first thing that I can do is to figure out the voltage across the inductor. And I want to point out right now, I do a lot of copying and pasting in my PowerPoints. This should actually be an L, not an R, right? So the voltage across the inductor in phasor notation can be written as the amplitude, which is 1.05 over the square root of 2, and the voltage has a phase angle of 120, so that's 0.742 with a phase angle of 120. I also want to be able to write down what the impedance is for the inductor. So the first thing that I'm going to do is I'm going to figure out what is the reactance of that inductor for this particular circuit. And so the circuit is oscillating with an angular frequency of 50 rads per second, and if I multiply that by 0.5 Henry, I end up getting 25 ohms. So the inductive reactance in this circuit is equivalent to 25 ohms. That's how much it's resisting the flow of electricity. So now I can write down what my impedance is for this inductor. So the impedance is just the reactance with an angle of 90 degrees. And so that means it's 25 ohms with an angle of 90, or I can write it in rectangular form as just having an imaginary part of 25 ohms. So why do I need the impedance? I need that because I'm going to figure out what the current is through the inductor. And the current, according to the equivalent of Ohm's law for AC, is just the voltage over the impedance. I know what the voltage of my inductor is, 0.742, phase angle of 120. My impedance is 25 with an angle of 90. 120 minus 90 gives me 30. And then I can divide the quantities out front and I get 0.0297 amps at an angle of 30 degrees. If I want to write this back in terms of sinusoidal form, I have to take the effective value in my phasor notation and multiply by the square root of 2. And then I can write this as sine omega t plus the angle of 30 degrees, which gives me 0.042 sine omega t plus 30 degrees. And the one thing that I notice is that the voltage across the inductor, which has an angle of 120, is leading the current through the inductor by 90 degrees because this is 30. And how do I see all that? Well, one of the things I see is that my impedance has an angle of 90 degrees. And so that impedance of 90 degrees tells me that through that component, the voltage is going to lead the current by 90 degrees. So that angle for the impedance is actually very important. I can make a plot of these, and so I have my plot here for my voltage varying sinusoidally. It's shifted to the left by 120 degrees. So this is a little bit harder to see, but basically here's the 0 axis. Here's where the sine function would start at 0 if it could, so that's shifted 120. My current is shifted by 30, so it's shifted over here. This one is 30, and the angle between them is 90 degrees. It's easier to see in phasor notation, as we know. So here's our voltage in the second quadrant at 120 and our current at 30 degrees. So it does seem like a lot of work to get to these answers, rather than just using the fact that I know the voltage leads by 90, so I can easily plug those values in. But the idea is that we're building up these ideas of impedance so that we can look at more complicated circuits.